At 8:14 in the morning on January 5, 1943, Lieutenant Red Cochran stood behind a 5-inch anti-aircraft gun on the cruiser USS Helena, watching 4 Japanese dive bombers pull away from their attack run. The bombers had already struck. One had scored a direct hit on the New Zealand light cruiser Achilles sailing alongside. The raid was over. The Japanese were leaving. Most gunners would have let them go. Cochran did not. He ordered his gun crew to open fire on the retreating aircraft. It was almost a casual decision, an afterthought. The bombers were at extreme range, tiny dots shrinking against the morning sky over Guadalcanal. Hitting them with conventional anti-aircraft fire would require either incredible luck or divine intervention. Cochran had neither. What he had was something the Japanese did not know existed. His gun crew fired 3 salvos. One of those shells passed within 70 feet of a fleeing ID-3A dive bomber and exploded mid-air. The bomber disintegrated. The pilot never knew what killed him. Neither did Japanese intelligence. Neither did most of the American sailors watching from nearby ships. They had just witnessed the combat debut of one of the most closely guarded secrets of the Second World War, a weapon so classified its existence was protected at the same level as the atomic bomb. It was called the proximity fuse, and it would change the nature of warfare forever. Before the fuse, anti-aircraft warfare was brutally inefficient. On December 7, 1941, when Japanese planes attacked Pearl Harbor, American gunners faced an impossible problem. To shoot down an aircraft with conventional shells, you had to hit it directly. No near misses, no estimates. Traveling at hundreds of miles per hour, moving unpredictably in 3-dimensional space, the odds were terrifying. Military analysts estimated it took between 1,000 and 2,000 shells to destroy a single plane. In some cases, 20,000 rounds were fired for just one kill. The guns themselves were not at fault. American 5-inch anti-aircraft artillery was accurate and powerful. The problem was the fuses. Contact fuses required a direct hit. Time fuses exploded after a preset number of seconds, relying on gunners to calculate the aircraft's altitude and speed perfectly. Even small errors meant missed targets. During Pearl Harbor, thousands of shells were fired, yet almost no enemy aircraft were destroyed. Many shells fell back to the streets of Honolulu. Civilians were killed by their own country's anti-aircraft fire. 49 people died, including infants and entire families. The math of anti-aircraft warfare before the proximity fuse was deadly and unforgiving. In Washington, a physicist named Merle Tuve believed he could change that. Tuve had no military experience, no artillery training. He was a scientist at the Carnegie Institution, studying cosmic rays and the Earth's magnetic field. Yet he asked a simple, radical question. What if a shell could sense when it was near a target and detonate automatically? What if the shell itself made the target 50 times larger by eliminating the need for a direct hit? The concept had stumped engineers for years. British and German scientists had tried, but the technical challenges seemed insurmountable. A proximity fuse required a tiny radar set, a complete radio transmitter and receiver, small enough to fit in the nose of an artillery shell. It had to survive being fired from a gun, experiencing forces 20,000 times greater than gravity, spinning at 25,000 revolutions per minute, and operating in rain, wind, and salt spray. Most critically, it relied on vacuum tubes, fragile glass devices that shattered under the slightest shock. In 1940, Vannevar Bush,
head of the National Defense Research Committee, tasked Tuve with solving the problem. Tuve assembled Section T, a small team of scientists, and posted rules on the lab walls. "I don't want any damn fool in this laboratory to save money. I only want him to save time. Shoot for an 80% job. We can't afford perfection. Don't try for an A. In a war, D is necessary and enough, but F is fatal. The best job in the world is a total failure if it is too late." Breakthrough came from James Van Allen, a young physicist from Iowa. He realized that the fragile filaments inside vacuum tubes were breaking not from the glass, but from internal stress during firing. His solution: suspend each filament on a tiny spring to absorb the shock. The filament stayed intact under extreme forces. Suddenly, the impossible became possible. With the filament problem solved, the team integrated a miniature generator to power the fuse, activated only by the shell's spin. The fuse emitted radio signals, detected reflections from nearby aircraft, and detonated at the point of closest approach. No direct hit was needed. One shell could now create a lethal sphere of destruction around an aircraft. When Cochrane's gunners fired that morning, the result was immediate and decisive. The bomber disintegrated, unseen and unheard until the explosion. The technology, now proven in combat, would be deployed widely across naval and later ground artillery. Efficiency skyrocketed. Where thousands of shells had been needed before, now a few hundred sufficed. Aircraft that had once slipped through anti-aircraft fire could no longer survive. The Japanese called it invisible death. The impact on the war was profound. During the Battle of the Philippine Sea, proximity-fused anti-aircraft shells decimated Japanese carrier aviation. Hundreds of planes were destroyed in minutes. On land, airburst artillery transformed defensive tactics, rendering trenches and foxholes far less effective. By war's end, millions of shells had been fired with the technology, saving countless American lives and contributing directly to strategic victories across the Pacific and Europe. The proximity fuse solved a mathematical impossibility with brilliant engineering. It transformed artillery into a weapon of certainty. And in that single moment at 8:14 a.m. on the USS Helena, the future of anti-aircraft warfare and the course of the Second World War was changed forever.
He sketched the design on paper, a minute coil spring wrapped around a mandrel, with one end of the filament welded to the spring's free end. The spring would maintain nearly constant tension on the filament during the violent acceleration through the gun barrel. It would also shift microphonics outside the amplifier's frequency passband, preventing false signals. Van Allen handed the sketch to a technician named Wood, who executed the idea using the microscopic assembly skills of the women who built hearing aid vacuum tubes. The scheme worked. The tubes survived. But vacuum tubes were only one of dozens of engineering problems that had to be solved. The fuse also needed a power source. Conventional batteries of the era were too large and too unreliable. Worse, they lost charge while sitting on warehouse shelves, making them useless for ammunition that might be stored for months or even years before firing. The National Carbon Company, a predecessor of Union Carbide, developed a revolutionary solution. They created a battery that remained inert until the instant the shell was fired. A fragile glass ampule filled with electrolyte was surrounded by stacked metal plates. When the shell was fired, the tremendous acceleration shattered the ampule. The shell's rapid spin then forced the electrolyte outward into the plates, instantly creating a working wet cell battery. This reserve battery had an almost indefinite shelf life. Ammunition could be stored for years without losing effectiveness, activating only in the moment it was fired. Safety posed another critical challenge. The fuse contained a detonator connected directly to the shell's main explosive charge. If it activated too early, the shell could explode inside the gun barrel or immediately after leaving the muzzle, killing the gun crew and destroying the weapon. Engineers responded with multiple redundant safety systems. The battery would not activate until several milliseconds after firing, ensuring the shell had traveled a safe distance. The shell's spin was also used to arm secondary safeties. Components were intentionally misaligned, so they would only lock into firing position after the shell reached full rotational speed. Early testing revealed dangerous failures. Some fuses detonated prematurely, exploding far from any target. Investigation showed the oscillator tubes were picking up interference from their own filaments. The original dual filament design produced beat frequencies that generated microphonic noise within the amplifier's passband, triggering false detonations. The fix required switching to a single filament oscillator tube. It was a minor design change, but it took months to identify and implement. Every delay meant more American sailors dying under Japanese air attack. Testing expanded nationwide. At the Naval Proving Ground in Dahlgren, Virginia, thousands of shells were fired across the Potomac River. At a test site near Socorro, New Mexico, shells were fired at aircraft suspended between towers. Kirtland Army Airfield conducted nearly 50,000 test firings between 1942 and 1945. Each test revealed new problems. Moisture caused circuit failures, heat damaged components, centrifugal forces distorted antenna geometry. One by one, solutions were found. Electronics were potted in wax and oil to distribute stress. Mounting points were reinforced. Manufacturing tolerances were refined until the fuses could survive forces that would instantly destroy civilian electronics. The Sylvania Electric Company became essential to the program. Their expertise in miniature vacuum tube manufacturing, developed for the hearing aid industry, gave them unique capabilities. Sylvania established multiple facilities dedicated to proximity fuse production, including a plant in Ipswich, Massachusetts, where hundreds of women assembled delicate tubes by hand. These women worked under extraordinary secrecy. They were searched when entering and leaving the plant. Purses and personal items were forbidden. Even local police and fire departments were barred from entry. Many worked for years without knowing what they were building. Some believed they were making light bulb components. Others assumed radio parts. One worker later recalled, "We were told it was important war work. We were told lives depended on us doing it right, but we were never told what it was. Not until after the war ended did we learn we had been building the proximity fuse." Secrecy extended across the entire production chain. More than 2,000 suppliers contributed components, from chemical manufacturers to precision machine shops. Most had no idea how their parts were used. This compartmentalization was deliberate. If any single worker or company were captured or compromised, they could reveal nothing useful to the enemy. By late autumn of 1942, the first Section T radio proximity fuses rolled off the production line. Each contained roughly 130 miniature electronic components, including 5 of Van Allen's spring-mounted vacuum tubes. The entire assembly fit into the nose of a 5-inch naval shell. The fuse operated on a simple principle. A small radio transmitter continuously broadcast a signal using the shell's metal body as an antenna. When the signal reflected off a nearby aircraft, a receiver detected it. As the shell closed in, the reflected signal grew stronger. When it reached a preset threshold, typically around 70 feet, a thyrotron tube acted as an electronic switch, releasing energy stored in a tiny capacitor. That energy triggered the detonator, exploding the main charge. The shell did not need to strike the aircraft. A near miss was enough. In August 1942, the Navy tested the fuse aboard the light cruiser USS Cleveland during its shakedown cruise in Chesapeake Bay. The targets were 3 remotely controlled pilotless drones performing evasive maneuvers. All 3 were destroyed on the first day using just 4 bursts of proximity-fused ammunition. The Navy canceled the remaining 2 days of testing. There was nothing left to prove. Production began immediately. Contracts went to Crossley, RCA, Eastman Kodak, General Electric, and McQuay Norris. Eventually, more than 100 factories participated, employing thousands of workers, most of them women, assembling components by hand. None were told what they were building. The program's security classification matched that of the Manhattan Project. By late autumn of 1942, the first naval 5-inch shell equipped with the radio proximity fuse emerged from the assembly line. Each contained roughly 130 miniature electronic components, including 5 of Van Allen's spring-mounted vacuum tubes. The entire assembly fit into the nose of a 5-inch naval shell. The fuse operated on a simple principle. A small radio transmitter continuously broadcast a signal using the shell's metal body as an antenna. When the signal reflected off a nearby aircraft, a receiver detected it. As the shell closed in, the reflected signal grew stronger. When it reached a preset threshold, typically around 70 feet, a thyratron tube acted as an electronic switch, releasing energy stored in a tiny capacitor. That energy triggered the detonator, exploding the main charge. The shell did not need to strike the aircraft. A near miss was enough. In August 1942, the Navy tested the fuse aboard the light cruiser USS Cleveland during its shakedown cruise in Chesapeake Bay. The targets were 3 remotely controlled pilotless drones performing evasive maneuvers. All 3 were destroyed on the first day using just 4 bursts of proximity-fused ammunition. The Navy canceled the remaining 2 days of testing. There was nothing left to prove. Production began immediately. Contracts went to Crossley, RCA, Eastman Kodak, General Electric, and McQuay Norris. Eventually, more than 100 factories participated, employing thousands of workers, most of them women, assembling components by hand. None were told what they were building. The program's security classification matched that of the Manhattan Project. By late autumn of 1942, the first naval 5-inch shell equipped with the radio proximity fuse emerged from the assembly line. Each contained roughly 130 miniature electronic components, including 5 of Van Allen's spring-mounted vacuum tubes. The entire assembly fit into the nose of a 5-inch naval shell. The fuse operated on a simple principle. A small radio transmitter continuously broadcast a signal using the shell's metal body as an antenna. When the signal reflected off a nearby aircraft, a receiver detected it. As the shell closed in, the reflected signal grew stronger. When it reached a preset threshold, typically around 70 feet, a thyratron tube acted as an electronic switch, releasing energy stored in a tiny capacitor. That energy triggered the detonator, exploding the main charge. The shell did not need to strike the aircraft. A near miss was enough. In August 1942, the Navy tested the fuse aboard the
carriers Enterprise and Saratoga and the light cruiser Helena were identified as the ships most likely to face Japanese air attack. Each received a carefully guarded allocation of the new ammunition along with strict instructions on its use. D. Parsons, the naval ordnance officer instrumental in the fuse's development, personally accompanied the shipment to the Pacific. He consulted with Admiral William Halsey on which vessels faced the greatest threat and supervised the distribution of the precious shells. On January 5, 1943, the proximity fuse entered combat for the first time aboard the Helena. Lieutenant Cochrane and his crew brought down a fleeing Japanese dive bomber with a weapon the enemy did not even know existed. The engagement was almost anticlimactic. The Japanese aircraft were already leaving after their attack, and one had scored a hit on the Achilles. The raid was essentially over. Cochrane's decision to fire at the retreating bombers was as much about training his crew as stopping an immediate threat. Yet those few shots changed history. The bomber that fell was the first aircraft ever destroyed by a proximity fuse in combat. The kill proved that the weapon worked as designed, that years of development and testing had produced something that functioned in the chaos of battle. Word spread quickly through the fleet. Within weeks, other ships began receiving allocations of the new ammunition. Gunnery officers trained by Van Allen and Parsons taught their crews the tactics for employing the weapon. Confidence in American anti-aircraft defenses began to grow. Over the following months, the results were dramatic. Before the proximity fuse, Navy gunners needed 1,000 to 2,000 rounds to bring down a single enemy aircraft. With the new fuse, that number dropped to around 250 rounds per kill, even against kamikaze aircraft flying straight and level toward their targets. The improvement was even more striking. By 1943, although only about 25% of anti-aircraft ammunition issued to the fleet had proximity fuses, those shells accounted for roughly 50% of Japanese aircraft shot down by naval fire. The fuse was roughly 300% more effective than conventional time fuses. By 1945, that ratio had climbed to nearly 600%, despite about 30% of proximity fuses failing to detonate. The Japanese noticed a change, but they could not understand it. Pilots reported American fire seemed more accurate, more lethal. Aircraft were being destroyed without apparent hits. Intelligence officers examined wreckage, interrogated captured American air crews, but could find no explanation. Some Japanese commanders guessed American shells were equipped with improved time fuses. Others speculated about magnetic detection. None guessed the truth. The concept of a self-contained radar set small enough to fit inside a shell's nose was beyond their technological imagination. Japanese anti-aircraft development had pursued other avenues. Acoustic fuses triggered by engine sound, electrostatic fuses detecting electrical fields, none proved effective. The radio proximity fuse required miniaturization, precise manufacturing, and mass production capability that Japanese industry could not match. Germany faced the same problem. German scientists had experimented with proximity fuses since the 1930s, developing over 30 designs. But wartime strain, two-front conflict, and Allied bombing prevented them from producing sufficient quantities of precision components. The proximity fuse was not only clever engineering, it was a triumph of industrial organization. Converting a laboratory prototype into millions of mass-produced weapons required unprecedented coordination between scientists, engineers, manufacturers, and the military. Vannevar Bush, who oversaw the American wartime research effort, later called the proximity fuse one of his proudest achievements. The Office of Scientific Research and Development coordinated 30,000 scientists across 300 universities and research facilities. The FUSE program alone involved over 100 manufacturers and thousands of subcontractors. Axis powers could not match that organizational capacity. Germany had brilliant scientists, but their programs were isolated and competed for resources. Japan had skilled craftsmen, but lacked the mass production infrastructure for millions of precision electronics. The proximity fuse was an American industrial achievement, demonstrating what coordinated scientific research and manufacturing could accomplish.
Meanwhile, in Europe, the fuse's impact was about to become even more dramatic. In June 1944, 1 week after the D-Day landings in Normandy, Germany unleashed the V-1 flying bomb against Britain. Known as the buzz bomb or doodlebug, the small pilotless aircraft carried an 1,800-pound warhead, flew at nearly 400 miles per hour at around 3,000 feet, and was too fast for most fighters and too small for conventional anti-aircraft guns. Between June 13th and late August, approximately 9,300 V-1s were launched from the French coast, averaging 120 per day. Over 2.5 months, the missiles killed nearly as many British civilians as the Blitz of 1940 to 1941.
Conventional defenses quickly proved inadequate. Fighter aircraft could intercept some V-1s, but the missiles were extremely dangerous to approach. Shooting one down risked being caught in the explosion. A few pilots developed a desperate technique, flying alongside the V-1s and nudging them with their wingtips to disrupt the gyroscopic guidance system and send the bomb into an uncontrolled dive. It worked, but it demanded extraordinary skill and courage, and cost lives. Anti-aircraft guns were even less effective at first. The V-1s flew at the edge of effective gun range, and their small size and high speed made them nearly impossible to hit with time-fused shells. During the first week of the campaign, anti-aircraft batteries in the coastal gun belt achieved only a 17% destruction rate. Thousands of shells were fired for every missile destroyed. The threat to London was too severe to maintain the long-standing restriction on overland use of proximity fuses. On June 12, 1944, the combined Chiefs of Staff made a critical decision. They authorized proximity-fused ammunition for use over British territory. The effect was immediate and dramatic. Section T engineers modified the fuses specifically to target the small, fast-moving flying bombs. The revised fuses were installed in British 3.7-inch anti-aircraft shells and American 90mm ammunition. Batteries equipped with the new rounds were rushed to southern England. Within 4 weeks, the V-1 kill rate climbed from 17% to 79%. On one day near the end of August, anti-aircraft batteries using proximity fuses destroyed 82% of all incoming missiles. Ammunition expenditure fell from thousands of rounds per kill to roughly 100. Winston Churchill later reflected on the weapon's impact. He wrote that these so-called proximity fuses, made in the United States, proved extraordinarily effective against the small unmanned aircraft that assaulted Britain in 1944. The success in defending England led to another urgent deployment. In September 1944, British forces captured the port of Antwerp, the most important logistics hub supporting the Allied advance into Germany. The Germans immediately redirected their V-1 campaign against the port. Without Antwerp, Allied armies could not be supplied. It had to be defended at all costs. The V-1s attacking Antwerp flew even lower than those aimed at London, some at altitudes as low as 1,200 feet. This made them harder for fighters to intercept, but placed them squarely within anti-aircraft gun range. The problem was that the fuses optimized for higher altitude targets were less effective at these lower heights. Section T engineers worked on the clock to adapt the design. The modified fuses were rushed into production at the Crossley Corporation plant in Cincinnati, Ohio. Churchill personally authorized a special flight of Lancaster bombers to carry the new fuses directly from Cincinnati to Europe. It was an extraordinary decision, reflecting the urgency of the situation. The gamble paid off. When the first modified ammunition reached the batteries defending Antwerp, the results were immediate.
48 of the first 75 V-1s faced by a single anti-aircraft battalion were destroyed. The port remained operational through the winter of 1944 and 1945, ensuring that Allied armies received the supplies needed to continue their advance. Between October 1944 and March 1945, German forces launched 4,883 V-1s against Antwerp. Only about 12% reached the protected area. The rest were destroyed, many by shells equipped with proximity fuses. The defense of Antwerp demonstrated something essential about the proximity fuse program. It was not a single invention frozen in time. It was a living system, constantly adapted to new threats and conditions. Section T maintained a rapid development capability throughout the war, modifying designs as fast as the enemy changed tactics. Yet the greatest test of the proximity fuse was still ahead. On December 16, 1944, Germany launched its final major offensive on the Western Front. 300,000 German troops, supported by tanks and artillery, smashed into American lines in the Ardennes forest. The Battle of the Bulge caught the Allies completely by surprise. For days, American units were pushed back, surrounded, and overrun. Despite the crisis, General Dwight Eisenhower was initially forbidden from authorizing proximity-fused artillery over land. The fear of enemy recovery remained. But by December 19th, the situation was desperate. Eisenhower demanded immediate permission to use the weapon. 2 days later, all restrictions were lifted. 200,000 proximity-fused shells, codenamed PZIT, were rushed to the front. Just days earlier, General George Patton had attended a demonstration of the new ammunition. He watched shells detonate approximately 20 feet above the ground, showering everything below with steel fragments. The effect was devastating. Patton understood instantly what this meant for ground combat. He ordered the ammunition used against German forces near Ettelbruck, Luxembourg. On the night of December 25th and 26th, American artillery caught a German battalion crossing the Sauer River. The shells detonated 30 feet above the exposed troops, spraying shrapnel downward onto soldiers with no cover and no warning. By Patton's count, 702 German soldiers were killed in a single engagement. American infantrymen later called the proximity fuse a Christmas present for the Germans. Captured German soldiers described the attacks as sudden, violent bursts for which there was no defense. Artillery that once provided warning through the whistle of incoming shells now seemed to explode spontaneously in the air. Foxholes offered little protection. Shrapnel rained down from above, striking men who never saw it coming. German commanders offered rewards for any soldier who could recover an intact fuse. None ever did. The fuses were designed to self-destruct if they failed to detonate properly, and the few duds that survived buried themselves deep in frozen ground. The psychological impact was severe. Veteran soldiers who had survived years of combat lost confidence in their ability to survive in the open. Every movement between positions felt like an execution chamber. One captured German officer later said that his men believed American artillery knew exactly where they were and exactly when to explode. German intelligence examined fragments of recovered shells. They found electronic components but could not determine how they worked. Some scientists theorized infrared sensors. Others suspected acoustic triggers. None identified the truth. The concept of a miniature radar inside a shell remained undiscovered. This failure had strategic consequences. Germany could not develop countermeasures against a weapon it did not understand. Radio jamming failed because they did not know what frequencies to target. Decoys failed because they did not know what the fuses detected. The Battle of the Bulge marked a turning point not only in the war, but in warfare itself. For the first time, an electronic smart weapon had been used on a massive scale in ground combat. Artillery was transformed. Shells no longer needed direct hits to be lethal. Every round became a precision weapon, deadly across a wide area. After the battle, Patton wrote to Major General Levin H. Campbell, Jr., Chief of Army Ordnance. His letter became one of the most famous endorsements of any weapon in military history. "The new shell with the funny fuse," he wrote, "is devastating.
We caught a German battalion trying to cross the Sauer River and killed, by actual count, 702, Patton wrote. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." Patton was right. The proximity fuse had fundamentally changed the mathematics of artillery combat. Soldiers could no longer assume they were safe in the open. Every shell was now deadly across a much larger area. Dispersal and concealment became essential survival tactics. Secretary of the Navy James Forrestal offered his own assessment. The proximity fuse had blazed the trail to Japan. Without the protection this ingenious device provided the surface ships of the fleet, the westward push could not have been so swift, and the cost in men and ships would have been immeasurably higher. By the end of the war, American factories had produced over 22 million proximity fuses at a cost of roughly $1 billion, about $15 billion in today's currency. The cost per fuse dropped from $72 in 1942 to just $18 by 1945 as mass production techniques were refined. The program remained classified throughout the war. Japanese and German soldiers died by the thousands without ever understanding what was killing them. It was not until September 20th, 1945, weeks after Japan's surrender, that the existence of the proximity fuse was revealed to the public. The scientists and engineers who created it received little public recognition. Merle Tuve returned to the Carnegie Institution and resumed his research in geophysics, never seeking fame for his wartime work. James Van Allen went on to discover the radiation belts that now bear his name, using instruments launched aboard early American satellites. Few knew that his first great contribution had been a tiny spring inside a vacuum tube. The Applied Physics Laboratory at Johns Hopkins University, created specifically for the proximity fuse program, continued operating after the war and remains active today. In early 1942, Section T had outgrown its space at the Carnegie Institution. Tuve negotiated an arrangement with Johns Hopkins to establish a dedicated research facility. The university rented a 3-story building in Silver Spring, Maryland, which had formerly housed a garage and Social Security offices. This unlikely location became the birthplace of one of America's most important defense research institutions. By 1944, the Applied Physics Laboratory employed over 700 scientists and engineers. D. Luke Hopkins, a member of the Johns Hopkins Board of Trustees, threw the full weight of the university behind the project. Equipment, lab space, and administrative support flowed to the fuse program. The partnership between academic research and military necessity produced results that neither could have achieved alone. The women who assembled the fuses deserve special recognition. Across America, from Massachusetts to Ohio to California, thousands of women spent the war years performing microscopic assembly work that required extraordinary patience and precision. They wound tiny coils, mounted miniature vacuum tubes, and soldered connections so small they required magnifying glasses. Many developed eye strain and repetitive stress injuries. The work was tedious and exacting, yet they persisted day after day, knowing only that their efforts were important to the war effort.
When secrecy was lifted in September 1945, these women learned for the first time that they had helped build one of the war's most important weapons. Some received awards, but most quietly returned to their pre-war lives, their contribution known only to themselves and their families. Commander William S. Parsons, the naval ordnance officer who served as liaison between Section T and the Bureau of Ordnance, later became famous for a different reason. He was the weapons officer aboard the Enola Gay on August 6, 1945, responsible for arming the atomic bomb that destroyed Hiroshima. His earlier work on the proximity fuse is largely forgotten today. The fuse technology itself continued to evolve. Modern proximity fuses use solid-state electronics instead of vacuum tubes, sophisticated radar systems, and computer-controlled timing. Some employ laser range finding or multiple sensing technologies for greater reliability. Yet the fundamental principle remains the same. A projectile senses its distance from a target and detonates at the optimal moment to inflict maximum damage. This concept, born in Merle Tuve's laboratory and perfected by Van Allen and thousands of engineers and factory workers, revolutionized warfare and continues to shape military technology today. Admiral Lewis Strauss, who served on the Manhattan Project Oversight Committee and later chaired the Atomic Energy Commission, offered perhaps the most succinct assessment of its importance. While no single invention won the war, the proximity fuse must be listed among the very small group of developments, alongside radar, upon which victory very largely depended. Historian James Finney Baxter III wrote that if one looks at the program as a whole, the magnitude and complexity of the effort rank it among the 3 or 4 most extraordinary scientific achievements of the war. Yet the proximity fuse has largely been forgotten. The atomic bomb commands far more attention. Radar is widely credited with winning the Battle of Britain. The proximity fuse, despite saving countless lives and changing the nature of warfare, remains obscure. Perhaps this is because it killed rather than threatened. The atomic bomb ended the war through the mere promise of destruction. Radar provided warning, allowing defenders to prepare. The proximity fuse simply made death more efficient. It turned near misses into kills. It made artillery deadlier without making it more visible. There is no monument to the proximity fuse. No museum exhibit tells its story in full. The women who assembled the tiny components have mostly passed away, many never knowing what they helped create. Yet the principle lives on. Modern missiles and smart weapons use direct descendants of the technology developed by Section T. The Patriot missile system that intercepted Iraqi Scud missiles during the Gulf War employed proximity fuse technology. Most contemporary air-to-air missiles, surface-to-air missiles, and precision-guided munitions do as well. Every time a modern weapon detonates at exactly the right moment to destroy its target, it is using principles first demonstrated aboard the Helena on that January morning in 1943. The proximity fuse was not glamorous. It was not dramatic. It was a marvel of engineering hidden inside the nose of an artillery shell. But it represented something profound about how America fought the Second World War. It showed that scientific innovation, mass production, and sheer determination could create weapons the enemy could neither understand nor counter. And it proved that sometimes the most important innovations are the ones nobody sees coming. If you found this story compelling, take a moment to like this video. It helps share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories. Each one matters. Each one deserves to be remembered. Leave a comment below telling us where you are watching from. Our community spans from Texas to Tasmania, from veterans to history enthusiasts. You are part of something special. Thank you for watching and for keeping these stories alive.